Okay, I'd like to go over your most recent IU style test with you, and as I do that, I'll try to make general comments that help as you review for the test. I'll be reviewing backwards and forwards a little bit on Calculus in a Nutshell, which I still strongly recommend that you take a look at um, and read through. I've added some pages to it. So on our first problem, we got the quotient rule here because I rewrote the originals so I could see them better here. It's y equals x over x plus 1. It's the quotient rule. And off of one of my new pages on Calculus in a Nutshell, there is your quotient rule. Square the denominator, write the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Or as we said in class, low d high minus high d low over the square of what's below. So here we've got the denominator squared, the denominator written, the derivative of the numerator, x, the derivative of x is 1, minus the numerator written down times the derivative of the denominator, and we've got it there. It said not to simplify, so just quit. Okay, our next problem is a chain rule problem. In fact, it's a chain rule problem really with 3 levels. And right here off of Calculus in a Nutshell again, in one of the new pages, the derivative of f of g of x. Here we've got an outer function and an inner function. You differentiate the outside function first. You leave whatever's on the inside alone, and then you take the derivative of the inside. You keep doing that until you have differentiated everything. So here we have y equals the cosine of x squared plus 1 to the third. Okay, the outermost function is raising to the third power. It's what you do last if you're evaluating it. So we're going to differentiate the third power function, leaving the inside alone. That will bring us to this. We're going to differentiate the cosine function, leaving its inside alone. And finally, we're going to differentiate the x squared plus 1 function. So we get, okay, the derivative of anything cubed is you bring the power out front. You leave the inside alone now, and you lower the power by 1, making it squared. Now we're going to differentiate the cosine of x squared plus 1. The derivative of cosine anything is negative sine of that thing. Again, we leave the inside, the x squared plus 1 alone. And finally, we multiply times the derivative of x squared plus 1, which is 2x. Our next one, we've got the product rule, because we have two things that are being multiplied. Again, I've written it over here. That's x times e to the negative x squared. And the product rule right here. In the product rule, you leave one term alone, and then you take the derivative of the other, plus whichever one you differentiated the first time, you leave it alone the second time, and then times the derivative of the one that you did not take the derivative of the first time. So in each part, you take one derivative, leave the other term alone, and you add in the middle. Okay, so what I'm going to do is I've taken this x and I've just written him down. Now I'm going to take the derivative of my second term, which is the e to the negative x squared. Okay, now that's going to be, we're to an e rule now. The derivative of e to the anything is e to the anything. So the derivative of e to the negative x squared is e to the negative x squared. But by the chain rule, you have to multiply by negative 2x. Over here, this time I'm leaving the e to the negative x squared alone and multiplying times the derivative of x, which is just 1. Off of my list here that shows the chain rule derivatives, find my e guy to show you what that was. When I took the derivative of e to the negative x squared, the negative x squared was the u. That was going to be e to the u, which is e to the negative x squared times, and what u prime is, that's just another way of writing times u's derivative du dx. That was the place here where I multiplied by the negative 2x. Okay. This is the fundamental theorem of calculus, part 2, that tells us that we can take this derivative anytime you see the constant up to a variable, or in this case a variable expression. The first step is to fill in that x squared, just put it in the place of the t. So you get x squared cubed. So that's a little hard to read there. That's x squared cubed, that's filling the x squared in for the t, plus 1. But because that's an x squared, it's not just a plain old x. You have to multiply times the derivative of x squared, which is 2x. This last step, which is showing up very light, so I'll emphasize that there, all I did was simplify x squared cubed to the x to the 6th. It's an optional step for you. Okay, first page done. On the second page, we are integrating, and we've got our basic power rule here for integration coming up next then. And it says that, well, first of all, when you integrate a sum, three things added together, you integrate each part separately. Now, this guy needs to be rewritten as x to the 1/2 power so I can apply my power rule for integrals. This guy I'll leave alone because that's a special case. The integral of 1 over x is going to be ln absolute value of x. And that needs to, this guy over here needed to be rewritten as x to the -2. So now we've got, our rule says for integration there, and I'm here on the page I've added in to calculus in a nutshell, that you integrate u to the n, you add 1 to the power and divide by the new power, unless n was -1, and that's our special case with ln x. So, here we go. This is the 1/2 power, and again, I'll try to emphasize where those were not dark enough before. I think they show up okay on the computer screen, but on my little thing here they're not. So I'm going to add 1 to the power. That's going to make that 3/2, and I divide by 3/2, which is the same as multiplying by 2/3. My next one, this is 2 times, the constant just tags along for the ride, the integral of 1 over x, which is ln absolute value x by one of our rules. And now I'll add 1 to the power and divide by the new power, which gets me this. I think you could have left it there because it said don't simplify, but I made this negative from the -1, 1 over x, from x to the -1. We have some videos on u substitution on Prism that you might want to look at if you've forgotten any of this idea. Again, here I've rewritten the original. We don't have a rule for this. We can look at our rule sheet, but there's nothing for it. The idea then is to make a substitution that turns it into something I have a rule for. Okay, so I'm going to let u equal the 3x squared minus 1 in hopes of turning this into e to the u, which should be our favorite integral because the integral of e to the u is e to the u. So if u is 3x squared minus 1, then the derivative of u, which is what this means, we're just putting, it's like du dx, but we're going to put the dx over there. The derivative of u with respect to x is, bring that power out, 6x dx. Well, I don't quite have what I want yet, okay? But I'm close because here's an x and a dx. So if I would just rewrite the original a little bit, I'm going to put at the end where it wasn't before a 6 next to the dx, because if I would combine this x right here with this guy, 6dx, I would have 6x dx, which is my du. Now, when I put that 6 in, I had to compensate with a 1/6 out front. This now becomes 1/6 e to the u with respect to u. And the integral of e to the u is e to the u. That's our favorite one. And you just replace the u with the 3x squared minus 1, and you've got your answer. This last one kind of threw us for a loop, because we had seen this on our chapter, our integration chapter test, and I recommend you go back and look at all your chapter tests because they'll have styles of problems that maybe didn't appear here, but are valid things for the final exam. And I said that in my email last week to you. Look at your old tests, look at your AP problems that were similar, okay, that had, not similar, but covered integrals, in different ways. We know integrals give us areas, for instance. What were those problems like? Okay, now we've got this critter, and we're going to make a little u substitution. we're going to put u in the place of x plus 1 like before, because we don't have a rule for the way this looked before. Now, what we're going to do then, du and dx are the same, so that's easy. But what you have in that case is you have a leftover x that isn't used anywhere. Here was the trick, if you'll remember. You take this expression and solve it for x, just by subtracting 1 from each side. The x gets replaced with the u minus 1, and the square root of x plus 1 becomes the square root of u, or u to the 1/2 power. So now you just distribute the u to the 1/2 through there, and that gets you here. And now you're going to apply your power rule twice. We raise 1 to the power and divide by the new power. Remember, dividing by 5/2 is multiplying by 2/5. Minus, we add 1 to the 1/2 up here, getting 3/2. Again, dividing by 3/2 is multiplying by 2/3. We put the x plus 1's back in the place of the u, and we've got our answers. Okay, so here's a fact we need to know. We have a lot of rules, and none of our derivative rules handle this case directly. When we're doing x to the n is a real number. When we're doing a to the x, a is a real number. So our problem is, what happens when you get a variable in both the base and exponent of an expression? See, we've got the sine of x, that's in a variable, it's a function, raised to another function, not just a number. This is when you have to use logarithmic differentiation. This part I'll explain later. It's just keeping our answer safe. You didn't really have to consider that, but I'll show you where it comes in. So your first step in logarithmic differentiation, if it wasn't written as y equals, is to let y replace f of x. And this was our original problem up here. And now, after you've done that, then it's called logarithmic differentiation because you take the natural log of each side. That's your beginning. Now, one of our properties of natural logarithms, and if you don't know them, you'll want to review those. One of our properties of natural logarithms is that you can bring this x out front. So this becomes ln y equals x ln sine x. So the advantage is I no longer have a variable base with a variable exponent on it. I just have a product. Now you differentiate implicitly with respect to x, which means on your x terms, everything's going to be as normal. But when you differentiate the ln y, you're going to get a derivative. You're going to get over here, the derivative of ln anything is 1 over that thing, and then times the derivative of y is dy dx. That equals. Okay, on the right side, these are all x terms, so it's just life as normal when I take the derivative with respect to x. Product rule, I write the x down. I take the derivative of ln sine x, right? And the derivative of ln anything is 1 over that thing. You multiply then times the derivative of sine x, which is cosine x. Yeah, just looking for my little derivative page there. Under my new page, I added into Calculus in a Nutshell. Let's see if we can find that guy real quick that we used on ln. And we'll find him somewhere. Oh, it's right here. The derivative of ln u, and they've just written it this way. They put the u prime there. We would write it's 1 over u times u prime is the way we would probably show that one. Okay? Which means you do 1 over u times u's derivative, u prime. There we go. Okay, so on back to where we were, we've got 1 over sine x, that was the 1 over u, times u prime cosine x. Remember, we were doing the derivative of ln sine x. Now plus, now we're going to do the derivative of the x term up here and leave the ln sine x alone. Okay, so we've differentiated implicitly. Okay, on our next one then, next step, we're just basically solving for our dy dx. So we're going to multiply this y right here over to that side. This is just cleaning this up, and you don't have to write that as cotangent. You could have written it as cosine over sine, but cosine over sine is cotangent x. And then plus ln sine x from that term over there. Last step, rewrite y as sine x to the x, and that's because that's what it started off as. I think I may not flip back and forth to calculus in a nutshell so much because I'm wasting time and it might be confusing. Okay, so here we'll go. We'll just assume that you're going to read that document. Okay, so now we've got on this guy that f of x is the integral. Well, no, what we had was f prime of x equaled e to the 2x plus 1, and we have a value of the original function. We're supposed to find the original function. Okay, so we've got that if you're at the first derivative, you'll integrate to get to the original function. We need to do that integral, and most of you did that pretty well. It was another u substitution. You let u be 2x plus 1, and then du is 2 times dx. Okay, now what we normally showed in class was I'd put a times 2 there and a 1/2 out front. Okay, and now that's why there's a 1/2 in the next expression, and the 2 times dx just got replaced with du over here. Well, this is going to be 1/2 e to the u du, which is the integral of e to the u is e to the u, and you plug back in the 2x plus 1 that you equaled. Now, they wanted us to find the value of c. This is like 3/4 of our problem, but we have to get the rest of it. We're going to use this fact to find our value of c. We're going to say that 0 equals what I get when I plug ln 4 in for my x that's right there. That gets us to here. Okay? Now, the next step is the one that most people mess up on or didn't get. Okay, you can rewrite this expression as this expression, and all you're doing is using a property of exponents. Okay? If you had a to the m plus n, ugly n, you could rewrite that as a to the m times a to the n, because when you multiply like bases, you add the powers. Well, that's what's going on here, so we're working it backwards. We've got these guys added, so I can write this as e to the 2 ln 4 times e to the first. Now, I could use my properties of logarithms that says I can bring that power up over the 4 and make that ln 4 squared. Well, 4 squared is 16, and that gets me to here. Now, e to the ln 16, since e to the x and ln x are inverses, is just plain old 16. A half of 16 is 8, and now I solve this. C is negative 8e, and there is the end of my problem. Okay, my limit page comes next. And on this first one, this is a just plug it in limit. That's our first choice, is if you can just put in that's limit x approaches 3. You can see that better on your paper. Oh, there it is. Limit x approaches 3. If you just plug in all the 3's and evaluate it, you just get the number 3 as your answer. Okay, on our second one. Now, this is the limit as x approaches 1 of 1 minus x squared over x squared plus 5x minus 6. Well, the deal is if you plug in the 1, you get zeros top and bottom. So you have two choices. You could use L'Hopital's rule, or you could factor and cancel. I chose to factor and cancel. Alrighty. So when I factor the 1 minus x squared, it factors into 1 minus x, 1 plus x. When I factor the x squared plus 5x minus 6, it factors into x plus 6, x minus 1. Now, you're looking for a cancellation, and you've almost got it on these two terms. If you factor negative 1 out of 1 minus x, that's negative x minus 1. There's your cancellation. You cancel out the x minus 1's, and that gets you here. The negative still remains, but you have an x plus 1 left from the top and an x plus 6 on the bottom. Now you plug in, you're going to 1, you just plug in your limit, and you're done. Okay, we're taking the limit to infinity on this guy. And remember, our basic way, if we are doing these limits, is that we're going to infinity is dividing by the highest power of x in the denominator, which would just be plain old x. But you got that square root of x squared term up top, which is a little bit of a problem. Now remember, as that the square root of x squared is the absolute value of x, which means for positive numbers it's x, but for negative numbers it's the opposite of x. Well, that first page of calculus in a nutshell, by the way. As x approaches infinity, x would have to be bigger than 0, so the absolute value of x is plain old x. I'm going to divide the denominator terms by x. The numerator is going to be divided by the square root of x squared, which means I'm under the square root, I'm putting x squared. So I put x squareds under every term that was in the square root. That's dividing the top by the square root of x squared. And I put plain old x's in the denominator. Okay, do a little simplifying, and that gets me to here. Now, as x approaches infinity, all the terms with x in the denominator are going to go to 0. That goes to 0, that goes to 0, and that goes to 0, which leaves you with the square root of 9, which is 3, over negative 1. Your answer was negative 3. By the way, the ABCDs were scrambled, so don't go by the ABCDs, go by the answers that we're showing. Okay, on our last one. The easiest way, I think, to deal with this guy is just to rewrite him. E to anything to a negative power is the same as 1 over that thing to a positive power, e to the positive x squared. And as x goes to infinity, e to the x squared is going to infinity, just like e to the x would be. Now you've got 1 divided by something to go into infinity, your quotient is going to 0. All right, I think what we'll do, well, we'll just try to continue, I guess. I think maybe I will just, these videos take a while to upload, so I'm going to stop this one, and I'll pick this up in a second video in a second.